ये जो मटेरियल मैंने आप लोगों को भेजा लेक्चर नंबर 12 एंड 13 का, इसको मैं जो है वो अब एक्सप्लेन करूँगा। तो हमारा जो पहला सेक्शन है वो है ट्रांसफॉर्मेशन लॉज फॉर कार्टेशियन कंपोनेंट्स ऑफ वेक्टर्स। तो आई एम एक्सपेक्टिंग कि आप लोगों ने जो प्रीवियस लेक्चर्स थे वो पढ़े होंगे। तो इसमें हमने क्या करना है, हमने जो है वो ट्रांसफॉर्मेशन लॉ जो है वो फाइंड करना है फॉर द कंपोनेंट्स ऑफ वेक्टर। सो लेट अस सपोज दैट वी हैव वेक्टर ए and we can write its components with respect to basis ei, as it is written ai equals to a dot ei. So we can write its component with respect to another basis ei dash, which can be written as ei dash equals to a dot ei dash. So now what we have to do, we have to relate ai and ai dash, that how we can move from unprimed system to a primed system. We know that our bases are related with this equation which is there, which is written ei dash equals to qmi em, where qmi are the components of our transformation matrix. So using this in above equation, we can write ai dash equals to a dot qmi em equals to, since qmi is a scalar, so we can take it out, so we can write a dot aem. So simply we know that a dot em is simple am. So we have equation 2b 12.1a. This is the transformation law for the components of vectors, that if we have given a vector with respect to basis ei, then with the help of this transformation law 2b12.1a, we can write components of that vector with respect to basis ei dash. Obviously transformation matrix will be given. So this 2b12.1b is the matrix form of previous equation. So we can write 2b12.1c from 2b12.1b. that you can see that this is only the transpose of your transformation matrix Q, which you have already obtained in your previous lecture. So there is one thing which you must know, the difference between a matrix A and dash and matrix of a dash. Thus here you can see that the distinction is that a and a dash are the matrices of the same vector with respect to different bases. Means that this is the matrix of vector a with respect to basis ei, and this is the matrix of same vector a with respect to basis ei dash. But these two are different things, where a and a dash are two different vectors. A dash being the transformed vector of a through any transformation matrix. So as we know that this transformation matrix is orthogonal, so we can write 2b12.2a from 2b12.1c by simply operating with q on both sides. So this equation also can be written from 2b12.2a. So this is the example that if we have given a vector A with respect to basis EI, so how can we write its component with respect to EI dash, where we have given that our EI dash can be obtained with a rotation of 90-degree counterclockwise about E3 axis. So simply we have to find Q. So first you can write E1 dash equals to E2. So this thing you can write with the help of your previous lecture, in which you have written the transformation matrix. Simply where you can use the angle theta is equal to 90, and you can have E1 dash equals to E2 and E2 dash equals to minus E1, E3 dash equals to E3, because we are taking rotation about x3 axis. Also you can simply see that if you will move from E1 to E2 with a 90 degree angle, then your E1 dash will be parallel to E2 and your E2 dash will be parallel to minus E1. This is given in the next page here, figure 2.5. So we can write Q from this. So first column will be 0 1 0, second will be minus 1 0 0, and third will be 0 0 1. So use this formula, A dash equals to transpose of Q into A. Simply you have components of A with respect to basis EI dash. So now we will extend this to our tensor, transformation law for Cartesian components of a tensor. You can write the components of tensor T with respect to basis EI in this equation. Tij equals to EI dot Tej. So with respect to basis EI dash, its components can be written as T dash Ij equals to EI dash dot Tej dash. Keep in mind that there is no dash on bold T, because this is tensor and tensor is the same. So in similar fashion you can write EI dash and put in above equation. Simply QMI EI dash, instead of EI dash you have written QMI EM dot EJ dash EJ, and instead of M you will use N, because you know that these two are dummy indices, and dummy index can't be appear more than 2 times. So take the scalar outside QMI Q and J, then we can write EM dot TEN, and EM dot TEN you can write it as TMN. Now this is the transformation law for the components of a tensor, that if you have components of tensor T with respect to basis EI, then with the help of 2b13.1a you can have components of tensor T with respect to basis EI dash. So 2b13.1b is the matrix form of 2b13.1a, and then again 2b13.1c. So you can move back from dash to undashed. So we're simply operating with the Q, because you know that Q is orthogonal. So use identity for Q transpose Q or Q transpose. This is again simple example that for given tensor T with respect to basis ei. Find components with respect to ei dash, and ei dash is again given as an example, previous example. So simply you have to write q, and simply you have to multiply these three matrices, and you will have t dash. Now this is an example which is telling us that TII is invariant quantity with respect to the change of basis. Invariant means that its value will not change. Now invariant that we have to show simply that TII dash equals to TII dash. That if you add the diagonal components of t before transformation and after transformation, then its sum will remain same. This is what we are saying in this example 2/13.2. We know that we can write ti dash equals to qmi qnj tmn. Simply you will replace j by I on both sides. So if you remember, qmi q and qni will be equal to delta mn, orthogonality condition. Ti dash, and here there will be delta mn. Again they both are dummy indices, so we can write tmm. So we can this can be written t11 dash plus t22 dash plus t33 dash plus equals to t11 plus t22 plus t3. You can apply this on your previous example. Here you can see that your t has t11 0 plus 2 plus 1 equals to 3. Here t11 dash 2 plus 0 plus 1 equals to 3. So you can see that trace remains invariant with respect to any change of basis. This example is asking to find the t12 dash for the tensor t and the basis ei and ei dash. So there is another way. In this example we are telling that there is another way to find the any component of t dash with respect to basis ei dash. So we are taking the same example 2b13.1, where you have e1 dash equals to e2, e2 dash equals to minus e1. So t12 dash can be written as e1 dash dot te2 dash. Now this thing is coming from here. Simply t12 dash equals to e1 dash dot te2 dash. So simply put e1 dash here, e2 dot e2 dash is minus e1. We can take minus out. e2 dot te1. So this is a minus t21. This thing is equal to t21. So what is t21? t21 is given in 2b13.1, that is plus 1. So t12 dash equals to minus 1. So this thing also can be found with the help of equation 2.13.1. That is simply the matrix form of this equation, which we have already used. So what is this? t12 dash equals to e1 dash t e2 prime. So this is e1. What is e1 dash? This is, so this can be written as 0 1 0 And what is t? T is given in your previous example, this one. And e2 dash, what is e2 dash? E2 dash is this minus 1 0 0. So simply multiply all this and you will have minus 1. Now we are in the position to define tensors with the help of transformation laws. As for we have defined our tensor with the help of linear transformation. Keep in mind that where we have defined only a second order tensor with the help of linear transformation, that if you have transformation, if it is linear, then we say that transformation is a tensor, second order tensor. Now with the help of this definition of tensor, you can define any tensor of any order. You can define any order tensor. So we will start, as we have already seen the transformation law of the components of vector, then we have seen transformation law of components of tensor. So we will generalize these two transformation law. So we have seen that ai dash equals to qmiam. So this is the transformation law for the components of vector, and this is the transformation law for the components of tensor, second order tensor. So now we will say that this vector is a first order tensor and this tensor is a second order tensor. And how we are saying that this is first and this is second? We will define order of tensor with the help of the free index, that how many free indices are present in the transformation law. Here you can see that there is only one free index, which is I. So it is first order tensor, which we are saying a vector. Now if we will see this transformation law, here we can say that we have two free indices I and j, so it is a second order tensor. So if we generalize this for a third order tensor, then this can be written as t prime ijk equals to qmi, qnj and qrk with t, m and r. That this transformation law is relating components of a third order tensor given in basis ei to the components given in basis ei dash, that how we can move from ei to ei dash for third order tensor. So this is first, this is second, this is third. Similarly you can move on 4th, 5th, 6th, 7th, 8th, 9th, 10th. Or simply what are these? These are simply components of transformation matrix. Simply components of transformation matrix. And that matrix simply transforming your basis ei to ei dash. It is written here, ei dash equal to q times ei. No. What is zeroth order tensor? If you move back, second order, first order, we are saying vector. Then what is behind the vector? That is scalar. Alpha dash equals to alpha, zeroth order tensor. Why it is zeroth order tensor? Because it has no free index. Third order has three free indices, second has two free indices, first has one free index. So zeroth must have zero free index. When there is no free index, it means that prime and unprime are same. That alpha dash equals to alpha, that scalar remains invariant in any n transformation. That if you have a scalar, suppose you have distance as scalar and then it remains invariant. If you are moving from ei to ei dash, its value will not change. So depending on these transformation laws, we have some rules, addition rule, that how we can add these. This is very simple. TIP, that if you have two tensors of third order, T prime ijk and S prime ijk, then they can be written as so addition or simply subtraction, only same order can be possible for this. So you can't add first into first order tensor with the second order or third order. This is a multiplication rule. If you have vector, these are the components of vector and these are the components of tensor T, and it's simply you have multiplied this ai. So in this product, how many free indices are there? There is no free index, so I is dummy, so it is a scalar. It will be a scalar. And if you take this type of product, then here there are three free indices I, j, k. This is the tensor of third order. Simply you can also take ai with tij. In that case you will have one free index j. So product of ai with tij will give you a first order tensor. This is a simple quotient rule. If ai are the components of arbitrary tensor, arbitrary vector, and aij are components of arbitrary tensor, and this thing is given ai equals to tij bj for all coordinates, then bi are the components of a vector. To prove this, we note. Now what we have to prove? We have to prove bi are the components of a vector. So we have to find some sort of a transformation law that we have seen in the previous page. Here, this type of transformation law we must have. As ai are the components of vectors, so this can be written as ai equals to qim am dash. This is equation number 1. And we know that tij are the components of tensor, so we can write equation number 2. Simply substitute equation 1 and equation 2 into the equation, this given equation. ai tij, and here it is not dash, it is simple bj. But this, we know that this equation holds for any coordinate, so we can write this equation for the prime coordinates. am dash equals to tmn bn dash. Or simply we have changed I by m and j by n, because we have already used I and j above. Thus equation number 3 becomes, put this equation number 4 into equation number 3, we can have equation number 5 simply without any change. am dash equals to this, and here we have right side. So multiply above equation with qik on both sides. qik, simply qik will be equal to delta km. Here will be delta km, and here also will be delta km, and m will be dummy with m, so it will be t dash kn. When you will use here qim into qik, then you can write that product as delta km. So again you will have delta km into t dash mn, and this m will be dummy with this m, so we can write t dash kn bn dash, same on the right hand side. You can take this on left side and you can write this, and we know that t is arbitrary, so parenthesis will be equal to 0, and we have the transformation law for the components of B for a, and this transformation law is for vector. So from this we can say that Bj are the components of a vector as required. Again, here we are generalizing the previous result, that if you have two tensors Tij and Eij and relating with this equation, then we have to show that this Cijkl is a tensor of rank 4. So this is an exercise for you. Symmetric and antisymmetric tensor. This is a tensor is said to be symmetric if transpose is equal to t, and components form we can write Tij equals to Tij, t equals to Tji. So if Tij equals to Tji for all ij, then we can say that the tensor T is symmetric, and for antisymmetric here you will have only minus. For antisymmetric tensor, you know that diagonal components become 0, because if you have Tij equals to minus Tji, simply 1 equals to minus T, so T11 equals to minus T11, then you can take its on right on the left side 2 times T11 equals to 0, so T11 equals to 0. No, 2b 15.3 is telling you that you can always write a tensor T into symmetric and antisymmetric part. This is the simple decomposition of a tensor T into symmetric and antisymmetric part. So what is the symmetric part? Simple T plus T transpose divided by 2, and antisymmetric is simple T minus T is antisymmetric part. So keep in mind that this composition is unique. So you need to prove this, that you need to prove the uniqueness of this decomposition. This is example related with symmetry and antisymmetry. That if you have a symmetric and antisymmetric tensor, then trace of their product will be equal to 0, and this is proved in this example. So you have to prove trace of TW, product of T and W equals to 0. Simple, you can write trace of TW equals to trace TW transpose with the help of your previous lectures. Simply here you will use the formula TW transpose and T transpose. Since T is symmetric and W is symmetric, so we can write. Again minus will be outside because trace is linear. So it will be minus trace TW. here we have used one fact which you have to write by yourself. I'm not going to tell you here. So it will be trace of w equals to 0. So exercise for this is the start from question number B17 to question number B28.